So calling convention. So what is a calling convention? And so pull up this a little bit. And so we have today, for example, we have function A, right? And function A may call function B with parameters A, B, C, and Z return value. So function or calling convention is simply a contract between the caller, in this case this function A is the caller, and the callee, which is the function that's being called. This would be function B. As far as how parameters are passed, are they in registers, are they in a stack, where the return value is passed back, and if you do use the stack during this call, who cleans it up? Is it the callee or the caller? So to start off with, let's go back to 16-bit, and we'll see why in a second here. So 16-bit, we had Windows Win16, and we had several calling conventions. I mean, I believe they even had fast call. They may have had this call back then. These ones we're going to get into when we talk about 32-bit, so ignore those for now. They had Fortran calling convention, which was similar to standard call, which we'll get into later, but except it had some weird parameters as far as pass by reference was how the only way they did parameter passing, but we're not going to talk about that. The two I want to actually talk about in 16-bit are cdecl, which is the C calling convention, and Pascal. Those are the two main ones I want to talk about. And again, we're going to get more into the calling conventions themselves when I get to 32-bit and 64-bit, because how many of you are actually going to use 16-bit? There's only a couple things I wanted to get across with this. And the first one is that in cdecl, standard C calling convention, you pass the parameters right to left, right? So C, B, A gets on the stack. Then you will get your return address pushed onto the stack. And that's how cdecl worked. And if you haven't seen my video on secrets of printf and you want to talk about variable arguments and why C calling convention is good for that, that's videos in the cards. So I'm not going to get into that in this video since I've already said that stuff in that video. So now the other thing about cdecl is that the caller, that would be function A, cleans up the stack. So you have C, B, A pushed on the stack. You put the return address. You call this function. This function does its stuff. It returns, and now you still have, you've cleaned up the calling. When you return, you clean up the return address, but these three are still on the stack. So now you've got to do an add, SP at the time, and if these are 16-bit, then it's 2 times 3 bytes that you would end up having to subtract there. Now in 16-bit, obviously back in those days, they didn't have that much memory. So, and not every function call required variable arguments, which is what this complete setup allows you to do, which again is in that other video. So they came up with using Pascal's calling convention. Now Pascal's calling convention pushed the parameters on left to right. So instead of CBA, it was A, B, C, and then return address. The second thing that Pascal calling convention provided was that the callee cleaned up the stack. And this was critical back then because this meant that instead of, so you would do a ret with a number of bytes to clean up the stack. So as soon as you return from this function, this whole stack was cleaned up. You no longer had to add another instruction after the call to add SP to clean up the stack, which means you save bytes. So before you had to call the actual function, and then you had to, when it returned, clean up the stack. So you have that entire block of code every single time you called. So you'd have to have the bytes to do the instruction to call, the bytes to do, the instruction to clean up, every single call. So by putting the call E to clean up, you now don't have to do that. You only have the bytes to do the actual call itself. The stack instruction to clean up is only, I think it's 3 bytes, and it's done within the instruction itself, so it's not duplicated, and so now you're only left with the call itself. So that's just the first thing I want to get across here, is that this is why you saw a Pascal calling convention a long time ago within Win16 programming. And Pascal actually, whenever Win32 came out, was redefined to be standard call or Win API. So now Pascal is standard call, which standard call, the only difference it really is that standard call pushes the parameters right to left like C, but it still cleans up the stack within the function itself. And we can get into that later. The last thing though that I wanted to say about 16-bit before we get into 32-bit is that whenever we had a stack and we ended up making a lot of calls, right? So we would say, return address, and the first thing we would always do is push BP and then move BP, SP. So we would move the stack pointer to the base pointer, and we would use the base pointer. This is previous base pointer. And then if you need another call, you do RA, previous base pointer, RA, previous base pointer. So this is the return address. This is the previous base pointer. And the base pointer would then be populated with this current stack location, so then the base pointer would be able to access the parameters, right? And so as you walk the stack, the current base pointer would point to the previous base pointer, would point to the previous base pointer, would point to the previous. So you got kind of a stack walk doing that. And 32-bit, they broke that a little bit because they didn't always save the previous base pointer. Now, one thing to realize about x86 assembly language and 16-bit, there were 2 registers. Well, there was also SI and DI, but BP and BX. So those 4 registers you could use as indexes. Now, these DI and SI use strings for certain, assembly code like move, SD and stuff like that. But BP and BX were the only ones that you could use as an index, which means that you could not reference SP directly and access memory. So you had to put the stack pointer into BP in order to access the stack. You couldn't just reference SP directly and access the stack. So you had to do this. Now in 32-bit, every register can be accessed as a pointer. So instead of just these 4 now ESP, EAX, ECX, EDX, they all can be accessed as pointer values. So you can put an address in them, you can access memory, whereas you couldn't do it before. You only had these 4 that you could do it with. So now that you could do it with any one, including the stack pointer, this was actually no longer required. Although they still kept this. Now it's gone completely away in 64-bit. But this is was not had to be done in 32-bit, so you would sometimes have functions that weren't doing it at all, and especially if it didn't have any parameters, they didn't have to do it. That was so. If you just walk the stack without symbol information, you wouldn't be able to walk everything. In 64-bit, they completely change it. They don't do this at all, and we'll get into that a little bit later. So the calling conventions of 32-bit are the following. So we have CDECL, and we'll show examples of these. So CDECL, C calling convention, and as I mentioned, Pascal went to standard call, which was the same as Pascal, where the call E cleaned up a stack, except for the fact that the parameters were pushed on like C, which is right to left instead of left to right, like Pascal. Right? And then we had fast call. So fast call is where the first 2 parameters are put in ECX and EDX, and then the rest are on the stack. And then we had this call. So if you're familiar with C++, whenever you call a member function that is non-static, it actually passes in an extra parameter as the first parameter, which is the this pointer or the object itself to that function, so it can work off the member functions or off the member variables and things like that. But this call would put the this pointer in ECX. So the this pointer would be in ECX and the rest would go regular on the stack. So we will take a look at these 32-bit calling conventions. We'll compile a program with all 4 of these, and we'll take a look at it. So as you can see here, we had to find this to be cdecl. So let's see what it looks like. And all right, so we have it here. Oops, I need to switch to 64-bit. Okay, I mean 32-bit. Yes. Okay, now here we go. So as you can see, we're going to push on EAX, where EAX is the address of a stack value. I'm going to push ESI, where ESI is the offset of this global color matrices. And if we take a look at the entry point here, let's take a look at the main. Okay, that's right. So there's the global, there's the stack value. So that is what we're passing in here. So we're passing in 2 values. Oops, right here, sorry. We're passing in these 2 values, calling this function, and then we are adding ESP. Right, 16. So if we unassemble this, take a look. To the end. There we go. We can see it's just a rat. And so that is the calling convention for cdecl. We push the parameters on, as you can see, right to left, and we end up cleaning up the stack. So, don't remember what it actually is to do fast call. Is it this? I don't think it is that. I don't think that's it. That is it. Okay. Add a parameter here in order to show that it's going to clean up the stack in a function call. So we'll come back here. We'll just add long x, and we'll just pass 10. Hopefully the compiler will realize we're not doing anything with it and won't optimize it out. All right, so let's see if we can compile that. Oh, 423. I didn't, I passed in 10. 423, what is it here? Oh, am I at the wrong? Oh, that's 64-bit build environment, oops. Okay, there we go. Wrong build environment. Okay, now. Switch to 32-bit. Since we're in 64-bit, we need to go to 32-bit WoW 64 compatibility mode and unassemble main again. Now let's take a look. Look at that. We're pushing on 10. We have the first parameter there, second parameter there. There's no cleanup here. That doesn't mean I couldn't optimize it and set it later. So let's check this here. We can actually do a UF. Just on this whole thing. There we go. Ret 4 this time. As you can see, this is a 3-byte instruction because it's C20400, which means we're removing 4 bytes from the stack, which is that 10 that we pushed on as a D word. Right, and if we did UF main, you can see it is just a C3, 1 byte instruction, and it's doing a ret and no stack cleanup. So, there you go. STD call, which I think also if we just did Win API, should be the same thing. Win API should be cast as the standard call macro. So that's why you see the Win API and all the Windows APIs, because that is the macro for standard call and not the intrinsic. So let's see if that works. Wow, 64. W unassemble color app main. And here we are. Now we've pushed 1 parameter, 2 parameters, and 3 parameters. And again, we went right to left. And there's no stack cleanup here. Let's take a look. We expect to see what? We expect to see a C2. As far as the ret machine code goes, a C2 with 4 times 3, which would be 12. So we expect to see a ret C. And that's what hopefully will come out of this. So let's, oops. So your main, let's come back up here and get this again. UF of that, and what do you know? C2 0C00, which is a ret C, which means remove 12 bytes from the call. So this is the calling convention, or standard calling convention, where you pass left to right, but the call E is who actually cleans up the stack. Being pushed on there again. Let me put it back into. Put back into 32-bit, but as you can see that it's putting the stack address, which is the this pointer for that class, as the first parameter. So we have 4 parameters. And again, since this is a this call, I believe I'll put this one as this call. And as you can see here, we have the ret 10. Now, back, come in here, take that and put it there. Alrighty. Okay, so now we have 1 parameter, 2 parameters, 3 parameters, and we're not putting that last one on the stack, we are putting it in ECX. And so that is the register it goes into, and that is why this one is a this call. And as you can see, we call this, and we then do this here, this ret C, to remove those 3 parameters. So that is the 32-bit calling conventions. The last thing here we want to talk about is 64-bit. And in 64-bit, we've got a new single calling convention. There's not a whole bunch of them like in 32-bit. And what they've done now is they've created it so that you allocate your stack at the beginning of the function. So if you have a function here, at the very beginning of that stack, you will at the very beginning of the function, you allocate the stack. And the stack is fixed now throughout the function, never changes. And so throughout this entire function, all the code, all the assembly code that's there, does not ever modify the stack anymore. Or they modify the stack, but they don't actually add or subtract to it. At the end of the function, then they clean up. And part of this, they will actually put this information into the binary itself. And that's how they stack walk. They'll take a look at your current RIP, and they know based on where you've set your initialization of the stack at, or the function, they'll know how much to take off of the stack to get to the next function. And they do that for every single function. That's the first thing. Second thing is there's no saving of RBP to be a stack hook anymore. It just uses a regular general purpose register. And they just use RSP directly to access everything. There's no indirection with RBP anymore, or the base pointer. It's just not done anymore. And the second thing is that every single function call always has 4 quad words reserved on the stack. Even if you have no parameters, you have to have 4 stack locations reserved for the function call. Nothing goes in them because your parameters are actually 4 registers: RCX, RDX, R8, and R9. If you have more than that, then they go on the stack at location 5, 6, and so forth. But no matter what, you always have this here, and in this location here, the call E is allowed to use those locations as scratch space, so it can actually save these registers there. So that's the first thing. Second thing is, REX as EAX, would return 32-bit, REX returns at 64-bit, and at the end, we always just do ret, and we clean up the stack for our own function. So that's how it's now done. Now, if you're passing or returning, if you're returning a floating point value, then it goes into XMM0. If you're passing in a floating point register, it goes in from 0, 1, 2, or 3. Now, or it goes on the stack after 5. Now, for example, if you're going to pass the first parameter as integer, second parameter as a floating point, then RCX would contain the integer, and XMM1 would contain the second parameter floating point. Now, if you're going to pass the first parameter as a floating point and the second parameter as an integer, then the first parameter would be XMM0 with a floating point, or the double, and RDX would be the second parameter. So they don't move their position. So XMM0 to 3 is the first 3 parameters, whichever one would have a floating point or none, and RCX, RDX, R8, R9 is the first 4 parameters. So now the next thing is, in 64-bit, you need to align the stack to a 16-byte value, which means the bottom nibble of the stack address must be 0. And every time you make a function call, you push the return address on the stack, which is a 64-bit number. So you're going from 0 to 8, which means that if you're going to make any other function calls, because it doesn't matter the kernel calls or interrupts or anything like that, because it's a separate stack. But for in the user mode, if you're going to make any function calls, you must at least pad the stack with 1 more quad word so that you're at a 16-byte boundary. This is because they allow you to, or it's assumed that you can optimize using aligned moves. For example, for XMM registers, there's aligned move instructions, like move APS. And if you do not do this, and you call a function that assumes that this is done, and does the aligned moves, which are faster than unaligned moves, it will create an exception, fault, and crash. So you must align your stack. And I'm going to show you some assembly code that does this. And we're going to take a look at one program, that's been built in 64-bit and does, and it shows this calling convention. But well, actually, we'll just show you the assembly, because we have written that in our assembly environment, which I'll link to in the description. So, if we're going to call this game init function, for example, we will pass RCX as our first parameter, RDX is of course our second parameter, and so those are the 2 parameters that are being passed into this function here. Now this function here, game load GIF, we're passing in RCX, RDX, as I mentioned. And you notice we always allocate our stack at the top, and notice we have this end prologue, which is what's telling the compiler how to interpret, this here as being our prologue, as far as after this location here, there's no more stack manipulation. And of course at the end, we always just do ret. So this is some of the code. This is what some of the code looks like when you're programming 64-bit. We're not using XMM in this call here, but if we were, then XMM would go into XM0. But let's take a look and see if we can find a function that uses more. Okay, here we go. So this function here uses RCX, RDX, R8, R9, and then it starts using the stack parameters. So, and there we go. So this tells you the unwind information. And as you can see, these are the parameters here. This is the starting address of the function. As you can see, that is the offset there. This is the end, and this is the location of the data for this that's being displayed here. So if we look, we have RBX. We have RBX at 60. RDI 28. As you can see, these are all our correct offsets for all these variables, or for all these registers being saved, and those are correctly in here. So then it's the last thing here is this alloc. And this essentially means you are from 8 to 128 bytes. And that's true. We are actually at 104 bytes. So how you look at this is there is an info, and info is C. So you take C, multiply it by 8, and add 8. And look, you get 104. And that's how you unwind the stack. What we're talking about here is, in 32-bit, we're talking about EVP pointing to the previous EVP. So for example, if I did DDS EVP L2, I would see the next one, and then I could do this here, L2, see the next one. So you can see I went from here to here. So if we unassemble this main here, we'll see that EVP is pushed and ESP goes in EVP. And remember I said that doesn't always happen. Now on 64-bit, what we're talking about here is this does not happen, right? So if we're in 64-bit here, I do a K, and now if I, again, look at the, none of these are putting EVP there, yet I'm still able to get the full stack walk. Now you may be thinking that, well, maybe the symbols are giving you that, since even 32-bit, the symbols would give you that on functions that aren't doing the EVP walk. And you would also be incorrect that that's the case. So then we can actually prove that. Let's take a look at this one here. So if you remember, I did a .fn ENT before, and we would look at, and we could take that parameter, 8 times 8 plus 8 is the, for this type, that's the formula. So you take the info times 8 plus 8, what we just did a minute ago, and we get 72 or 48. So that means that if I unassemble this, I better see 48 being subtracted, and I do. So that's the stack for this function. And so that's what helps you figure out the stack walk. Now you may be wondering, or you may be thinking that that's not true. Or how do I prove that? Like I said, .fn ent this. Now this is a location that's right here, right? And so it's E bytes. So again, let me do a K. Show you. Now we're at demo initialization, right? That's what we're looking at here. And we're looking at the unwind information in the binary. So if I do this and overwrite it, with just zeros. Now we'll do the same information here. And look at that, now we get some bad on 1 information. Well, what happens if I do K now? Oh, it's all messed up. In fact, let's assemble it and do db 0f. Whoop. Now what happens? See? Just by modifying those values are changing how the stack is walked. And so I remember here I actually had the original values here. So if I just did a EB, this and this here, I get it back to normal because I put the bytes back. And that is how the stack walk is done on x64. And it also has how exception handling is done. 32-bit exception handling is done a little bit differently. And there's a bang EX chain here, you can take a look. So maybe in a future video, we'll go over exception handling. But for now, that is it as far as calling conventions are concerned. 64-bit requires 4 stack spaces, even if you don't use them. And RCX, RDX, R8, R9 are the registers used for the first 4 parameters, if there's 4 parameters. And then the rest of the parameters are on stack. And the stack is pretty much allocated at the beginning of the function, and it's terminated at the end of the function. There's no, except for the alloc A scenario, there's no dynamic stack. And that is pretty much it for calling conventions. Alright, well, I hope you enjoyed this video on calling conventions, and maybe we'll talk about something else next time that may be more interesting than calling conventions.